Hi, my name is Dustin Yanofsky, and today we're talking about monoidal categories because this book is called Monoidal Category Theory. So we're up to page 238, and we're actually going to come to the definition of a monoidal category. So that's a lot of fun. Let's recap and put ourselves in context. So chapter 1 through 4 is about categories. Chapter 5 is about categories where you can combine things, okay? And we saw section 5.1 was about strictly associative monoidal categories, okay, where A tensor B tensor C is equal to A tensor B tensor C, where, you know, you put the parentheses the right way, okay, they're equal, okay. Then we had section 5.2 where we had Cartesian and co-Cartesian monoidal categories, which are about what? They're about a category with a product or a category with a co-product, and how those products and co-products, they give you they're not as strictly associative, but they give you automatically some other information. And today we're going to do section 5.3, which is called monoidal categories, and this is kind of the most general definition there is. We'll talk much later, next chapter we'll talk about where things are even less strict. Okay, even weaker. So in some sense, what you want to do is you want to think of strictly monoidal categories as strict. Okay, Cartesian categories are more general. Monoidal categories are more general. And later on, we'll see there's even more general. But for the rest of this textbook, we're going to be dealing with monoidal categories, and so this is important. Okay, so let's make a definition. Definition. A monoidal category is a category. Okay, and we're gonna endow this category with more structure. It's got a bifunctor, which is called a tensor product, or called a monoidal product. It's got a unit, it has an element in A, which we'll call a unit, but we have to show what it means to be a unit. So this is just like before, this is just like a strict monoidal category. Okay, but now we have requirements. Okay, so we're going to list off 3 different natural transformations. So alpha is going to be a natural transformation which takes which takes 3 elements. Okay, it's going to be a natural isomorphism. Okay, and this is going to be like this. It's going to take 3 objects. So a typical object is going to be alpha goes from A, B, C. It's going to go from A tensor B tensor C to, this is a component of the natural isomorphism, so it's an isomorphism, A tensor B tensor C, like that. Okay, and we had a name for such a thing. We called it a reassociator. Okay, again, same reason as before, it reassociates. Think of parentheses as associating different elements with different elements, so you're changing the association, and the ending tor, kind of like an operator, et cetera, et cetera. Okay, besides that, you have a left unitor. I always forget which way it goes. Hold on. Okay, so that goes from something tensor identity to the identity on A. So that takes so basically this goes, again, this is an isomorphism. So this is A tensor I isomorphic to A. Okay, so this is called a right. That's Greek letter rho. So this is the right unitor. Okay, and you have lambda which goes from I tensor to the identity. Okay, this does the exact opposite thing, the different thing. I tensor A goes to A. Okay, great. So you have these three natural isomorphisms, 1, 2, 3, left unitor, right unitor, and reassociator. Okay, and they have to satisfy some requirements. Okay, they have to satisfy some requirements. And we're going to go through these requirements because they're actually very important for the rest of the book. And the diagram I'm going to draw right now is probably the most fundamental diagram in all of monoidal category theory. So, you know what? We're going to get rid of this. And we're going to, because we're going to need all the room we can get. Okay? And so the next thing has a million names. It's called the pentagon condition. Or it's called, it has lots of different names. Pentagon coherence condition, McLean's coherence condition, Stasheff's coherence conditions. These were people who dealt with it. Okay, and what it's about is, and again, Pentagon coherence condition, okay? What it's about is not when you deal with A, B, and C, but what happens when you deal with A, B, C, D, when you have 4 different letters. So I'd like to draw it. Okay, A, tensor, B, tensor, C, tensor, D. Okay, so this has 4 things, okay, and this is identity, tensor, alpha of B, C, D, and so this goes to A tensor, that's on the outside, but we're going to rearrange the parentheses over here, and so this becomes B tensor C, tensor D, okay. And this goes to A tensor B, tensor C, tensor D. You know what? We got 2 more. A tensor B, tensor C, tensor D. A tensor B, tensor C, tensor D. Okay, so this is boom, BC. And this is boom, boom, boom. And this is okay. Now let's put in the names of the things. So this has BC as one object, okay, and so it's rearranging things. You have A, B, C, and D. So this is alpha of A, comma, B, tensor C, comma, D. Okay. This has D is in the outside, so this is going to be tensor ID of D, the identity of D, and this is rearranging A, B, C, A, B, C. So this is alpha of A, B, C. Okay, this has AB as one thing, and then it's rearranging C and D. So this is alpha of A tensor B as one thing, and then C and D. And finally, what's this? This has CD as one thing, and so this is usually done. This is alpha. A is one thing, B is one thing, and C tensor D is another thing. Okay, just notice you have all possibilities of one thing here, okay? So here you have CD, here you have AB, and here you have BC. All three possibilities are showing up, okay? And here you have identity on the outside, and here you have identity on the outside. That's identity of A, okay? Okay, now it's called a pentagon condition because a lot of times it's drawn like this. Boom, 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 boom. 1, 2, 3, 4, 5, boom, like this, or a diamond or something like that. Okay, and like I said, it's probably the most important diagram in this book, okay, the pentagon coherence condition. Okay, and basically what it says is that this alpha, this reassociator, has to get along with itself, okay? And so you have different instances of alpha, here, 5 different instances of alpha, and they have to get along with each other, and this has to commute. This diagram has to commute for all A, for all B, for all C, and for all D. So that's an important diagram. I didn't want to just write it, and I didn't want to just close the camera, have it perfectly on here. I wanted to develop it and show it to you. We're going to spend a lot of time talking about this diagram. This is the last time I'm going to write it, but in its full glory. But it's an important diagram, and what it shows is that these alphas get along. So basically, these 2 is equal to the composition of these 3. And so that's very nice. I didn't draw it as a diagram, but just because this is a lot neater for the book, but sometimes it's drawn like this, sometimes it's drawn like that. It's very good. Okay, that's one condition. So basically this says that alpha has to cohere with itself. Okay, so, but let's go through another condition that it has to be satisfied. And the other condition is that alpha has to get along with the unitors. Okay, and so that goes as follows. A tensor I, tensor B, A tensor I, tensor B. Okay, here you have an alpha. We're going to fill in the parentheses in a second. It goes like this, it goes like this, and this is A comma I comma B. Okay, and this is A tensor B, A tensor B. This goes like this, and this goes like this. Okay, and basically this is identity of A tensor. This is lambda of B. So the I tensor B shrinks down to the B, and this is rho of A tensor identity of B. Okay, so what this says is that alpha, the reassociator, has to get along with the left unitor and the right unitor. Okay, and so this this commutes. This is called the triangle coherence condition. Not the greatest name, but why not? Can't think of anything better. Okay, great. And that, my friends, is the definition of a monoidal category. Okay, nothing to it. So let's go through it. You have a category, a tensor product, a bifunctor, a unit. You have a reassociator, three different natural isomorphisms, a reassociator, a left unitor, a right unitor, and 2 conditions showing that they get along with each other. Okay, 2 coherence conditions, the pentagon and the triangle. Okay, and we're going to show a ton of examples in a minute. But before we go a ton of examples, there's something else to just make things a little bit more interesting. Okay, we're going to spend chapter 5, chapter 6, and chapter 7 all on different variations of monoidal categories. Okay, and we're going to see a lot of different types of monoidal categories, but we're going to start talking about one in particular, and that's called the symmetric monoidal category. And what that's about is, notice here we spent a lot of time talking about associativity. we didn't talk about commutativity. So we're going to spend time talking about commutativity. So let's make another definition. Definition. Okay. A symmetric monoidal category, a symmetric monoidal category is a monoidal category with a braiding. Okay, let me explain to you what a braiding is, but first let's just write out what it is. So it's the same thing. It's a category, a tensor product, a unit, a reassociator, a right unitor, a left unitor. Okay, but now something else, a braiding. Okay. Okay, and what's a braiding? Again, a braiding is not the best word for it, but we're going to follow convention. It's a braiding. So what's a braiding? A braiding goes from a pair of objects like that to, I think it's called twist. BR. Okay, we saw this in the last class, but basically this goes alpha, a component of this natural isomorphism is A comma B, which goes from A tensor B to twist the A and B, B tensor A, and then multiply them, B tensor A. Okay, so this is saying something about commutativity, A tensor B, B tensor A. Okay. Okay, so we added in a new natural transformation, okay? And we have to talk about what this new natural transformation deals with, okay? Okay, so we have a new operation and we want to see how this new operation, this braiding, how it gets along with the other things. Okay, we'll see later, we're going to talk about this. Coherence theory, or this type of thing, is sometimes called higher dimensional algebra. Okay, and the reason is because whenever you have an algebra, whenever you have a new operation, you know, you learn division, you want to see how division gets along with multiplication, how it gets along with addition, how it gets along with subtraction, etc., etc. So here too, we have this new operation, braiding. We want to see how it gets along with the other operations. Okay, and the answer is as follows. It has the following three conditions. Okay, we're going to write them all out. Okay, one is like this. A tensor B, B tensor A. This is gamma of A comma B. This is A tensor B. This is gamma of B comma A, and these two are equal. Okay? And what this says is gamma is its own inverse. Okay? In other words, if you flip things and you flip it again, you get the identity. Flip things and then flip it again, you get the identity. Okay? Once, twice, you get the identity. Okay, this has a name. It's called the symmetry coherence condition. Symmetry coherence condition. Okay, great. Let me give you a little bit out of the order. Okay, next, so what this says is gamma gets along with itself in some sense, and then we have A tensor I tensor A. This is gamma of A comma I. This is, what is it, rho or? This is rho of A. This is gamma of A. Okay? Okay, and this says this braiding should get along very well with the right unitor and the left unitor. Okay? This also has a name called the triangle symmetry condition. Okay, that's very nice. Okay, great. And now there's another two diagrams. The next two diagrams are called the hexagon conditions. Okay, so let's write them. These are called the hexagon coherence conditions. Okay, and basically what they're going to be about is about twisting lots of things. Okay, so but let's go through it. We had A tensor B, twist it, and then twist it again. You get the identity. Now we're going to deal not with two things: A B, twist, B A, twist again, A B. Okay, now we're not going to deal with that. Now we're going to deal with three things. And when you deal with three things, you can twist this, you can twist this, or you can twist this whole thing around this. Okay, but when you deal with three things, you also have to worry about associativity. Okay, so we're going to have to put that all into the mix, and we get two different conditions. Okay, and we're going to see this over and over again. Let's write it out. Okay, so this becomes A tensor B tensor C, A tensor B tensor C, B tensor C tensor A, B tensor A tensor C, B tensor A tensor C, B tensor C tensor A. Okay, let's put parentheses. B tensor C. This is B tensor A tensor B, B tensor C. Okay, good. Boom, 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 boom. Okay. 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 This is just a reassociator. It's alpha inverse of A. Usually they go like this. Usually the parentheses go from the right to the left. Here they're going from the left to the right. So it's A tensor B tensor C. Okay, did I write that right? Yes. Okay, now this, you have A and BC. You have BC and A. So this is gamma of A comma B tensor C. Okay, great. This is again B tensor C tensor A, B tensor C tensor A. This is the same thing, you just move the parentheses. So this is alpha minus 1, okay, of B comma C comma A. And then we're moving the parentheses here from the left to the right. Usually we go from the right to the left. So that's the inverse. Okay, let's do this. This is gamma of, we have the AB, we're swapping that. So this is A comma B. A tensor, the identity on C. Okay, BAC, BAC. So again, this is alpha minus 1 of B comma A comma C. Okay, and this is B is on the outside, and you're swapping AC and BC. So this is identity. Identity on B, tensor gamma of A comma C. Okay, great. Now, there's another one that deals not with alpha inverse, but with alphas. So let's do that. Ready? A tensor B tensor C. A tensor B tensor C. A tensor B tensor C. This is C tensor A tensor B. This is ACB, ACB. This is ACB, ACB. This is CAB. Okay, so again, hexagon, there are 6 maps in each one, hence the word hexagon. Okay, let's, without looking in the book, see if we can figure out what is going on. This is just regular reassociate, ABC, ABC, so this is a reassociator, A, comma, B, comma, C. This is swapping the C with the AB. So this is gamma of A tensor B, comma, C. This is identity of A tensor gamma of B, comma, C. This is alpha of A, comma, C, comma, B. This is AC, CA, so this is gamma of A, comma, C, tensor identity on B. Last one. This is alpha of C, comma, A, comma, B. Okay. So these two conditions basically say that gamma should get along with itself. In other words, whether you twist this or you twist around, here you're having one thing twist around two things. Basically what that says is that's twist one thing and that's twist another thing. Okay, we're going to see it more clearly in a second. But they also have to get along with the inverse, with the alphas and the alpha inverses. So that's what this is all about. Okay, great. Okay, now, there's a shorter version for this. Okay, so let's go through this. Monoidal categories deal with just associativity. Now we brought up in a new thing called symmetric monoidal categories, where we have not only associativity, but we also take care about commutativity. And so we had those 3 conditions. This is 2 different diagrams, so there's actually 4 conditions, okay, and we dealt with that. Now, let's say for a second, I don't want to deal with associativity. I want to think of my monoidal category is strict. What I mean by that is that the reassociator and the left unitor and the right unitor are all identities. They're equals, okay? Then how about this? What happens if I have commutativity, but not strict commutativity? A tensor B is equal to B tensor A, which we called strictly symmetric monoidal categories. I don't want to deal with that. I want to allow there to be a braiding, but it won't necessarily be like this. So in that case, these 2 conditions become much easier to write because you don't have to worry about parentheses. So let's write these 2 conditions in terms of just gammas, no alphas. So this is going to be, this is going to shrink down to A tensor B tensor C. That's this. Okay, and basically there's a map from that. So this is going to be a gamma of A, comma, B tensor C. And so this becomes A, no, sorry. This becomes B tensor C, B tensor C, tensor A. Notice no parentheses because we're assuming strict associativity. When you have strict associativity, like you do in addition and multiplication, you leave out parentheses because you know you can just multiply them any way you want. Okay, great. Now this is going to be the identity because the inverse of a reassociator is the identity. Okay, and let's do this. This becomes gamma of A comma B tensor identity on C. And so this becomes B tensor A tensor C. And now we go here. This goes up. This goes up. Okay. And what's this? This is identity of B, leave B outside, tensor AC BC. So this is gamma of A comma C. Okay, so let me just say this. This triangle is the same as this hexagon, but if you shrink all the identity, or shrink all the alphas, alpha, 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 to be 1 point, to be one, it collapses everything, and the what's it called collapses, the parentheses go bye-bye. Okay, let's do it for this one too. It's really important. So this becomes A tensor B tensor C. Okay, and we're gonna do this. This is gamma of A tensor B, A tensor B. Okay, that's different than before, comma C. So here we had gamma of A BC, and here we have A tensor B comma C, and so this becomes A tensor B, whoops, let's do that right. Okay, this becomes C tensor B, whoops, no, we have to follow. This becomes C tensor AB, A tensor B. CAB. Very good. Okay, now this is as follows. Again, so this is identity on A, leave A alone, tensor, so this is going to be A, okay, leave A alone, and this is going to be swap the B and C, so this is going to be tensor gamma of B comma C, and so this is A tensor C tensor B. Okay, and now leave the B alone, so this is identity on B, tensor CAB, AC, CB, so this is gamma of A comma C. Okay, so let's go through this again. You ready? In a strict monoidal category, in a strictly associative monoidal category, where you still have the braiding, you require these two things to be commute. Okay? Okay, now I just want to show you what they mean. Basically, you have three objects. Well, I should do this, we're going to do this later on anyways, but basically you have three objects. One says, look, I can cross these two objects with this one object. So cross this guy with this one object. Okay? Or that's the same thing as crossing this object with this object, and then crossing this object with this object. Okay, so that's what it's doing. You want to cross A and BC. That's the same thing as crossing A with B, and then crossing A with C. Okay, same thing over here. You want to cross AB around C. Well, that's the same thing as crossing B and C, and then afterwards crossing A and C. And you get that. Okay, so that's a very nice requirement. So we're going to have this over and over and over and over again. Okay, we're going to bring in a new categorical definition, a new structure. Okay, and the structures are going to consist of categories, functors, elements, and then natural transformations. Okay, and then we give coherence conditions. What's coherence conditions? Those are the conditions that the natural transformations have to get along with each other very well. Okay, and we're going to see a little bit later why we need these conditions, what they add to it, what we can do if they satisfy these conditions. That's the purpose. Okay, great. Okay, so far we saw the definition of a monoidal category, and we saw this definition of a symmetric monoidal category, and we saw the definition of a strictly associative symmetric monoidal category. A strictly associative symmetric monoidal category. Okay, great. Now lots of examples. As always, that's what we do. This book should be called Category Theory by Example. Okay, so first example, all strictly associative monoidal categories are monoidal categories. Okay, they are monoidal categories. And basically, the way they're monoidal categories, you say, oh, 1 second, we didn't deal, when we were in section 5.1, we didn't deal with all these alphas and rhos and lambdas. And yes, we did deal with them. They were just they were identities. Okay, so in strictly associative categories, those morphisms, transformations do exist, but they're identities. They shrink down. They say, okay, yes, there is a morphism from one to the other, but it's basically an identity, which means those two things are equal. A tensor B tensor C is equal to A tensor B tensor C. Okay, so that brings in to that's section 5.1. Okay. Okay, strictly associative. You know, I didn't call it that. Strictly associative. We can leave that word out. Strict monoidal categories are monoidal categories. Okay. Next, every. Okay. I was having all. So what's the difference? All, every. Right. Okay. All Cartesian categories and all co-Cartesian categories are monoidal categories. Oh, I'm sorry. Are symmetric monoidal categories. Okay, they're symmetric monoidal categories. Why? Because a Cartesian category had that braiding operation. Automatically, A tensor B is isomorphic to B tensor A. That satisfies it. Okay, now this is what section 5.2 is about. Now, there's something very much that has to be done here. Okay, namely, what we showed in Cartesian categories was when you have a product, A tensor B tensor C, A times B times C, A times B times C, okay? What we have like this was done way back in chapter 3, is we have an isomorphism. We'll call it A comma B comma C. Okay, for any A, B, C, you have such an isomorphism. Very nice. Which means there's a reassociator, okay? But who said that a product satisfies the pentagon condition? The Maclane's main pentagon condition, okay? And so what we have to do is we have to go through that and show that. It's done in the book. It's very, very technical because what you have to deal with is all the projection maps and show that they satisfy universal properties. Okay, so I'm not going to go through it because one has to see, you'll see it. It's not pretty. It's lots of projection maps. And what you have is, I call it a calculus of projection maps. Okay. And you have different rules about projection maps and the way they work and the way the products bring things together and take things out. So a little bit very, very technical, not hard, but a little technical. I'd like to show you basically what it's all about, okay? Rather than drawing that whole pentagon or drawing all those things, well, I'm just going to draw two parts of it, okay? Namely, A times B times C times D. If you have four objects, A times B times C times D, the pentagon, etc., etc. Okay, but main point. Okay. Main point is this is going to satisfy some universal property which only can be brought up with the product, and there's going to be a unique map from here to here following that thing. So that is the sum total of all the 2 or 3 pages of lots and lots of equations and showing about projection maps. But basically what that's doing is it's saying this, okay? When you have A, B, C, D, and you have A, B, C, D, there's a unique map from here to here, which gets along very well with the projection maps, and that's exactly what you have to show. Okay, it's a lot of work. It's not made for a classroom. It's made to sit and stare and look at it and look at it and look at it. And again, to get these ideas of the projection maps and how they interact with each other down clear. Okay? Okay, so, by the way, the same thing works with the coproduct also. Okay, so that takes a lot of work. Again, we're skipping that lot of work, but we're doing it. Okay, okay, another thought. So, I want to talk about the relationship between a monoidal category and a Cartesian category. So our first examples were Cartesian categories, but we're going to see Cartesian categories have universal properties, okay? And so we satisfy those universal properties, okay? And what you're going to spend a lot of time proving that Cartesian categories are monoidal categories, you're going to use those universal properties. But I want to say something else, okay? There's a much broader class of things called monoidal categories where the tensor, the bifunctor doesn't necessarily satisfy any universal properties. And so we have to assume they satisfy other axioms. And this gives us a much broader class of phenomenon and a much broader class of things that we can deal with. And we're going to show lots of examples. So yes, Cartesian categories are our first examples, but now we got off that and we can go on to many other things besides that. Okay, in some sense, Cartesian categories are very, very pretty. And strictly monoidal categories are even prettier. They're easier. Okay, so we're going to the broad outlines. So the way to think of this is as follows. You have strictly monoidal categories. Okay, and then you have Cartesian categories. I'm not going to talk about co-Cartesian categories. And then you're going to have monoidal categories. Okay, and this is a diagram we're going to see. We're also going to have to bring in monoidal categories, also have that, we have to worry about commutativity. Okay. Okay, let's continue with our list of many, many examples. There's one more difference that has to be stated, the difference between monoidal categories and Cartesian categories. A Cartesian category has a morphism for every object A. There's a morphism from A plus A. We call that the diagonal. Okay? This is going to be very important in Cartesian categories. Okay? Okay? It does not necessarily exist. We don't assume, it's not in any of the axioms that such a thing exists for a monoidal category. And this will have profound implications. Okay, great. Okay, so let's get busy. Now that we have all the definitions straight, let's get busy with two other interesting, important categories. Okay, one is called an association category. Okay, we write this as ASSOC, and this is going to be the paradigm of all monoidal categories, just monoidal. It's going to be a very important monoidal category, and I'll explain to you later on why it's so important. Now, this is a very simple category. The objects are words with parenthesizations. Okay? That's the objects. They're words with parenthesizations. So, well, not parenthesizations of letters, just of dots. Okay? Now, given two such things, or something like that. I don't know. This might not be good. Okay. Given two such parenthesizations, okay, then the tensor product of them is just put them together. Okay, so they're all things of this form. They're all just parenthesization of any number of dots. And the way to think of them is they're placeholders. The dots are placeholders for other letters. Now, we also want sometimes to have a placeholder for the identity. Okay, okay, great. Okay, so those are the objects. They're words with dots and identities, okay, and parenthesizations of them, okay. One second, what about the morphisms? Well, the morphisms are very simple. Given two such things, there's exactly one morphism between any two of them. We don't care how many ones there are, how many dots there are, et cetera, et cetera. You have a legitimate parenthesization here, you have a legitimate parenthesization here, there's a unique morphism from there to there, okay? Okay, great. The tensor product, we said, was just put two of them together, no problem. The tensor product of morphisms, well, you're going to take this morphism, you take that morphism, you're going to put them together. There's only one morphism to do that. Okay? This, by the way, this, I'm sorry, this is going to have a single identity morphism to this. So that's the unit. Okay, this is going to have a single isomorphism from here. There's one morphism there, there's one morphism there. So this satisfies. But the main thing is the pentagon commutes. Why? Because there's only one morphism from the beginning of the pentagon to the end of the pentagon. So it exists. There's exactly one morphism, so it exists, and it's very important. We're going to see why this category is very important. I call it the paradigmatic monoidal category. Great. Now, let's do something a little bit more complicated. Not the paradigmatic monoidal category, but the paradigmatic. Okay, so now we have something called the symmetry category. Okay, we'll denote it like this, SYM, okay, and this will be a category, which is the paradigm, and we'll explain what that means paradigm. What makes it so special? We'll explain that later on when we talk about morphisms between such things. Okay, paradigm of strictly symmetric, strictly associative, symmetric monoidal categories. Okay, so this category, sim, okay, will be it's going to be a strictly associative, okay, it's going to be a symmetric monoidal category. That means that we don't worry about the alphas. Symmetric monoidal category, we are worried about the commutativity, okay, and this is going to be the paradigm of it. Okay, so before I explain to you how you make up this category, we have to do a little background. So we have to talk about a little thing called symmetry groups. So we have to go to okay, and symmetry groups are types of groups, and they deal with permutations. Nothing complicated. So let's talk about S5. S5 is a symmetry group, okay? And basically what it does is it deals with permutations as follows. We're going to change this to something like this. 3, 1, 2, 5, 4. So this is a permutation of 1, 2, 3, 4. We do this, okay? The main point is as follows. If we have two such things, 1, 2, 3, 4, 5, goes to 5, 2, 4, 3, 1. Okay, we have two such things. Then a group has a multiplication, so we can compose this, and we can compose it as follows. So this times this is 1, 2, 3, 4, 5, and basically what we do is we do what this says, and then we do what this says. So let's see, 1 goes to 3, and 3 goes to 4. So this goes 1. Let's do that again. 1 goes to 3, and 3 goes to 4. So 1 is going to go to 4. Let's do that again. Let's do another one. 2 goes to 1, and 1 goes to 5. So that's going to be that. Okay, let's do this. 3 goes to 2, and 3 goes to 2, and 2 goes to 2. That takes care of that. 4 goes to 5, and 5 goes to 1. That takes care of that. And finally, 5 goes to 4, and 4 goes to 3. So that's composition. The composition of this map and this map is equal to this. Okay, so that's the group operation. The identity is the simplest in the world. It's this. Okay, namely 1 goes to 1, 2 goes to 2. It's the identity. You don't change the permutation. The permutation you keep the same. The pretty part of this is you can make a nice graphic way of doing this. So you have 5 dots. 1 goes to, and you have another 5 dots. Okay, 1 goes to 3, so that's like that. 2 goes to 1, that's like that. 3 goes to 2. That's like that. 4 goes to 5. That's like that. 5 goes to 4. Okay. Now let's see if we do both of these. Let's do this one. We might as well use the same 5 dots. Let's see. 1 goes to 5. That's like that. 2 goes to 2 goes to 2, that's like that. 3 goes to 4, that's like that. 4 goes to 3, that's like that. 5 goes to 1, that's like that. Okay, now when we compose that, look what we're going to get. We're going to get 1 goes to 4, so it's going to be 1 goes to 4, 1 goes to 4, which is exactly what we have here. 2 goes to 5, 2 goes to 5, which is exactly what we have here. 3 goes to 2, that goes there. 4 goes to 1, that goes there. And 5 goes to 3, that goes there. Okay, what does the identity look like? That's simplest. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. It looks like this. And when you compose with something like that, you get the same thing. You get the original. Okay, what about inverses? So the inverse is very simple, especially when you look at it like this. You just turn this upside down. So 1 is going to go to, so the inverse, let's do this. The inverse of this one is going to be from 1, 2, 3, 4, 5. Okay, let's see. 1 is going to go to 2. Okay. 2 is going to go to 3. 3 is going to go to 1. 4 is going to go to 5. 4 is going to go to 5. And 5 is going to go to 4. So that just flips this over. Okay, and so you get a group. You get a nice group. Okay, very nice. So it has inverses, etc., etc. It has, you can compose things. You have inverses, etc., etc. Okay, great. Now, each one of us, so by the way, we did this for 5, but you have S0, which is a very stupid group. It has only one element, I think, or maybe it has no elements. S1, which has one element. S2, that's a funny group because basically it has 1 goes to 2, there's the identity, and 1 goes to that. So it only has 2 elements, that group. Not a very interesting group, but you have S3, and you have S4, and you have S5. By the way, I didn't talk yet about the symmetry category, but here's the symmetry groups. Very nice. Okay, now let's talk about S6 for a second, but we can do it for any group. Okay, S6 is a way of describes all the ways of permuting 6 things. Turns out that this group has a lot of elements. Okay, I think 6 factorial elements. Okay, very nice. It has a lot of elements, but all the elements can be described with these few elements, with these few generators. So think of this as like the basis. Okay, we saw bases in linear algebra. But think of these are the things that generate, that make the entire group. Okay, there's these little atoms, if you want, that make the entire group. So here's 1. 1, 2, 3, 4, 5, 6. Okay, not too good with matching up. 1, 2, 3, 4, 5, 6. Okay, so we're going to call this little s1. That's an element in there. There's another group, another element to the group called S2, which is 1/111. 1, 2, 3, 4, 5, 6. Okay. There's another element, S3, which is 1/1/11. ... The last element, maybe we'll call it Sn or Sn minus 1, I don't remember, is 1/111/. Okay, so these generate all of S6. In other words, every element S6 can be written as a composition of these little things. In other words, when you want to change things around, you can change them with small micro moves one at a time. Okay, these little things satisfy three requirements, which will show up very importantly. Okay, namely, SI equals SI composed SI. So that's the operation. If you do it twice, I think what happens? You have cross the ith element, and you cross it again. So that's equal to the identity. Okay, we can see it right here. Let's do this one. Dum, 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 dum. Okay, this composed with this is equal to the identity. 6 elements. Okay, another thing, SI composed, and by this I mean group composition or group multiplication, Sj is equal to Sj composed Si. If I, the distance from I to j is more than 1. Let me just say what that means. That means if I swap these guys and then swap these guys, and they're far enough away from each other that there's no overlapping elements, I swap these two guys and I swap these two guys, that's the same thing as first swapping these two guys and then swapping these two guys. Okay, nice picture you can draw of this goes as follows. Okay, this is equal to, let's do it the right way. That's not the same picture, but it's the same, it represents the same permutation. So that's very nice. Okay, we're getting all the way down there. All right, good. There's a third relation, and it's given in the book on page 248. I don't want to draw it. It's very nice. You can see it right here, page 248. Okay, great. Okay, great. So these are the symmetry groups. There's an infinite number of symmetry groups, one for every natural number, and they go on and on. Okay, great. Now I want to talk about the symmetry category. Okay, so this is a category, and again, it's the paradigm of strictly associative. Okay, we have no parentheses here, but it is symmetric. The symmetric monoidal category. Okay, so the objects of this category are the natural numbers. Okay, and so we have 0, 1, 2, 3, 4, 5, 6, 7. Okay, that's the objects. And the morphisms, this is a little bit funny, the only morphisms here is S0, that's a group, but thought of as a one object category. Okay, S1, S2, S3, S4, S5, S6, Okay, so the only morphisms, you might think of this as a dot, 3 is a dot, and the only morphisms are around that dot. From S3, all the permutations of S3. And here you can have all the permutations of S5 around that one dot. Again, thinking of them as groups, so everything's invertible, etc., etc. I'm sorry, I forgot to say something very important about the associative category. It's also a groupoid. Okay, because every morphism is an isomorphism. There's a unique morphism. It's also what's called a collapsible groupoid, which means between any two objects, there's exactly one morphism. So there's no It's a nice category. Okay, this is going to be different. I'm sorry, I should have said that before. Okay, great. So this is the morphisms. Okay, and the idea is as follows. What's great? Now I tell you it's a monoidal category. So what is M? That's an object. Tensor. Okay, here's the tensor. Here's the operation. N. Well, it's equal to M plus N. Okay, great. That's on objects. So we're ready. We see it's strictly associative because addition is strictly associative. By the way, what's the unit? 0 is the unit. It has no morphism. So this is, I guess, the empty category, the empty group. Well, I don't know what it is. Empty or 1. Okay, you have to look it up in the book. Okay, next. Great. How about on morphisms? So here's a typical morphism in M. Okay. So this is going to be an object in S of M. This is going to be a morphism in S of M. So we'll write it like this. This is a morphism in S of M. Here's another typical morphism. Okay, morphisms only go from an object to itself. This is going to be an object in S of N. Okay, and we take the plus to that. Okay, great. So what does this morphism, when I take this tensor, this, what does it do? Well, basically, okay, it's going to do a permutation on M plus N numbers, and on the first M of those numbers, it's going to do one permutation, and on the second, and on the N, the rest of the N numbers, it's going to do another permutation. The way to think of this is with these pictures. You have M guys here, and you have some type of things going here. Very nice. Okay, there's M dots here. Then you have N dots here, and you have N dots here. And this is some type of permutation here. Well, boom, put them together, concatenate them, and you have a permutation of N plus N guys. Put them together. Okay, great. Okay. The associators and the unitors are all identity because this is an associative operation, okay? And the only thing to show is the triangle identities, and the triangle identities are very pretty, and we can show them right here. I'll show you two versions. This is on page 249. 1, 2, 3. 1, 2, 3. Okay, it goes as follows. Crossing, let's just write this as A, B, C, A, B, C. No, let's not write that A, B, C. Let's write this as A, C, B. Crossing A across these two things is the same thing as equals cross this with this, and the identity, and then cross this with this, and the identity. So I'll say A, B, C, and B, C, A. Okay? So doing one double cross is the same thing as doing two little crosses. That's one of them. The other one consists of going like this. Okay? Which is the same as this with the identity, and then this with the identity. Okay, main point. This double cross can be done by a composition of two single crosses. Now, this is for 3 strands, but it's not necessary for 3 strands. We could do this. This thing could correspond to M strands. This thing could correspond to N strands. This thing could correspond to P strands. Okay, and then you have, for the entire category, you have this thing. You have this satisfying the triangle identities. So, conclusion, sim is a strictly associative symmetric monoidal category. Okay, and it's a paradigmatic one. It's an important one. We'll see later on in chapter 6 when we talking about relationships between monoidal categories, what that means to be paradigmatic. Okay, but that's very important. Okay, great. What else? Hold on. Okay. Next. So that's an important category. Okay, let's look at another example of monoidal structure on a category. And this is K is a field, finite dimensional vector spaces. Okay, we already saw that that has a monoidal structure, namely it has a strict monoidal, no, it has not a strict monoidal structure. It has a Cartesian structure. Okay, let's just remember what the Cartesian structure was. That was this with the trivial finite dimensional vector spaces. That was one operation that we already saw. But now we're going to do another one, which is not Cartesian. And it's written like this, and K is the unit. Okay? Okay, so this is a finite dimensional vector space, and it works like this. Okay, let me show you how this works. Take a finite dimensional vector space, V. Take another finite dimensional vector space, W. Then there's a new finite dimensional vector space called V tensor W, and the word tensor is way overloaded in this book and in an entire field. So this is a tensor product of vector spaces. Very nice. Now I have to tell you how this is defined, so I'll do that, but it goes as follows. Let's say this is generated by a basis, B. Okay, so this has B1, B2, it's finite, so Bm. And let's say this is generated by a basis, we'll call it B prime. And this is equal to B1 prime, B2 prime, Bn prime. Okay, great. Now I want to generate this thing from a basis. So what this is a vector space, a finite dimensional K vector space. And I got to tell you what the elements are. Okay, so first I have to do is I have to make new elements. And so the new elements will be as follows. So this is going to be the basis. So we'll call it B hat or B bar. And this is going to be the basis of both of them. So again, the basis of V is this. The basis of W is this. Now I'm doing the basis of V tensor W. Well, the objects are going to be B1 tensor, it doesn't mean anything, B1 prime, comma, B1 tensor B2 prime, comma, B1 tensor B3 prime, dot, dot, dot. B1 tensor Bn prime, comma, B2 tensor B1 prime. Okay, comma, B2 tensor B2 prime, dot, dot, dot. So it's going to be all pairs, this guy's and this guy's. This guy tensor this guy's, okay? The last one will be Bm, not last because these are sets, we don't care about order, tensor B prime n. Okay? Okay, how many elements does this have? The number of elements in B hat equals m times n. Okay, I can write this as number of elements in B times the number of elements in B prime. Okay, great. That's the basis of it. So what's a typical element look like? Okay, and the answer is as follows. A typical element of this vector space is going to look like this. So let's write it as little v is going to equal to sum I equal 1 to m, j equal, sorry, we don't do I and j in this place, we do j and k. Oh no, we do I and j because we're not dealing with complex numbers. Okay, fine, well, it could be if you, fine. I equals 1, j equals 1 to n, okay, and then you're going to have a little k, we're going to have two subscripts here, ij, and this now we're going to have the element of the basis, and the element of the basis is bi tensor b prime j. That's what a typical element is. And you can add elements, and you can scale and multiply elements, etc., etc. A lot of details, etc., but we're just mentioning quickly. Okay, now there's a rule that these things have to satisfy, and we're not going to talk, we're going to mention it, but not go into the details of it. It's called bilinearity. Okay, we don't only want it to be linear, we want it bilinearity, which means linear in this one and linear in that one. You'll see the requirements in the book. Okay, great. That describes, given a vector space, given another vector space, we can create a new vector space called V tensor W. Great, but this works on a category. So we don't only have to worry about vector spaces, we have to worry about linear transformations. So let's do it. Ready? If you have from a linear transformation from V to V prime, and you have another linear transformation from W to W prime, then you can do T tensor T prime, which goes from V tensor W to V prime tensor W prime. And we have to go into details about how this is defined, but basically you can tell how it's defined. This T works on V, this T prime works on W, and they get the outputs they're supposed to get. Okay? What's K? K is the unit. K is the unit. So what does that mean? It means take any K vector space, finite dimensional K vector space, tensor it with K. By the way, how many basis elements does this have? This has one basis element, which basically looks like that. Okay? And so this is isomorphic to V, which means that that acts very nicely like a unit. Okay. Very nice. Okay. Very nice. By the way, we said it, but we have to spell it out. The dimension of V tensor W is equal to the dimension of V times the dimension of W, because we take the product of their two bases, the number of elements in each one of their bases. So we get a large, it's large. So this is different than what we saw before with the plus. When we were dealing with the plus, the dimensions were added. Here the dimensions are multiplied. It's much bigger, it's much more complicated. Okay, it is fundamental in all higher physics, and it's fundamental in all higher category theory. This category structure is fundamental. Okay, let's talk about some of those properties. So we know it's a monoidal category. I gotta tell you, it is not strictly associative, and you can see why, because if you had three of them, well, then the typical elements, you'd have B J prime tensor B K, I shouldn't use K, L M N O P P P double prime. Okay, that's a typical element if you do it on one side. Okay, but you're also going to have B J prime B. Sorry, there's a tensor there. There's a tensor there. There's a tensor there. B P double prime. You can also talk about that. Okay, these two basis elements are not equal. They are isomorphic in some sense, but whatever. And not they're isomorphic, but you can make a correspondence between them. And the tensor product of finite dimensional vector spaces is not associative. It's associative up to an isomorphism, and it satisfies the pentagon condition, so it's a monoidal category. In general, the tensor W is not equal to W tensor V. There might be an isomorphism. There's an isomorphism in between them. Yeah, but we're going to leave that alone. Okay, great. So a few quick more examples. It goes as follows. The book does another example with relations. I don't want to talk about it. It doesn't really show up again, but it's a nice example. It should be done. Next, we tell a property. This is a theorem. It's an important theorem, and it shows up. I'm not going to prove the theorem, but it's an important theorem. Take a monoidal category. Take a nice monoidal category. Okay? Look at the identity. So what you could do is you could look at endomorphisms of the identity. Okay? Lots of those. And we saw this already. Take any object in any category, the endomorphisms form a monoid. Okay? You can compose endomorphisms. Very nice. You can always compose endomorphisms. Okay? So it's a monoid. It's not necessarily a group, because not all endomorphisms are invertible, and the identity is definitely there, so it's a monoid, not necessarily a group. Theorem, and this shows up. The identity of a monoidal category, not only does the endomorphisms of I form a monoid, but it forms a commutative monoid. Okay, it commutes. Okay, and that's not trivial, and it's not typical in any category, but it is true in a monoidal category. Okay, and it's a little bit complicated, showing why it's true, but it's all done in the book. Great. Next, one more example. Take circuits. Okay, so the objects are natural numbers, and the morphisms, if this is from M to N, so this circuit has M input circuits and N output circuits. Well, if this has N input, and this has P outputs, then you can compose them, which makes the category of circuits a category. We saw that before. But not only is it a category, so that's what we saw before, but it's also a monoidal category. Okay, so if you have M prime inputs here and you have N prime inputs there, okay, then you can bring these together, and what you could say is this circuit, this whole circuit, both boxes, goes from M plus M prime inputs to N plus N prime inputs. That's very nice. Okay, it's very nice because this composition that we had before was sequential composition. You have sequential composition of circuits. Do one circuit, then do another circuit. This composition, which is the monoidal structure, is this composition of the monoidal structure is parallel processing, which is different than what we saw before. So that's very interesting. Okay, now question, does it have any more structure? And this is actually quite interesting. Namely, you might say, hey, maybe there's a way of doing that. Okay, so swapping your inverse, swapping your maps. The problem with this is, question, do these wires go on top of these wires, or do these wires go under these wires? Okay, and the answer is, this is different than this. Okay, and most importantly, if you swap them, let's do it this way. Okay, so here we have these wires are on top, these wires are below. Well, if you did this twice, you get, oh, I don't know. You get some knots. The main point is that knot is not equal to the identity. And what did we say about symmetric monoidal categories? That if you swap things twice, you get the identity. That's not the identity. That's swapping two wires. You get different wires. We're going to see later on, this is going to be fundamental in chapter 7, and it's going to be fundamental in a lot of other things. Main point, wires are very physical. You know, swapping two vector spaces, that's math. Wires are physical. When you get to physical things, it doesn't always work so nicely. And that's why we need more advanced types of monoidal categories. Okay, so that takes care of that. Have a wonderful day.